This is Chapter 9, Part 2 from the Essentials of Radiographic Physics and Imaging, 3rd edition. And this starts on page 102 with spatial resolution. So far we've discussed the two characteristics out of the four that make up a quality or diagnostic image. And in the last section, we talked about brightness and contrast and how those two factors determine making the anatomy visible. Because that's the first thing that you have to evaluate with an image, is that your image, the anatomy that you're imaging, is actually visible, tangible, that you can see it. And then we discussed that once you determine that your anatomy is visible, the second set of factors that you have to look at is how accurately you've imaged the anatomy that you've captured. So last session we talked about all the brightness and the contrast. This time we're going to talk about spatial resolution and distortion, which become the third and fourth factors that we actually evaluate once we have the sufficient brightness and sufficient contrast in an image. So we'll begin on page 102, and we will talk about spatial resolution. So when they talk about spatial resolution, basically we'll go back to the fact that an image is made up of information in the form of pixels. Remember we said that those are the square picture elements that are made up in a matrix. You have a matrix which are rows and columns of pixels, and each pixel is responsible for a section of anatomy, and that anatomy represents like a volume of tissue. And a pixel is two-dimensional, but it actually is imaging a three-dimensional object, which is in the human body. So it's actually representing a voxel of tissue. The matrix size, depending on the size of the matrix, the larger the matrix, the more pixels there are, and they're actually smaller, and the smaller the pixel, it gives you better spatial resolution. So the digital image is made up of discrete information in the form of pixels that display different shades of gray, because that's how it captures. When it captures the shade of gray, it's actually represented in numeric form in the digital image, and each number corresponds to a certain shade of gray. When we talk about spatial resolution, it's actually the accuracy of the structural lines that are recorded, and it's determined by not only the size of the pixel, but its spacing, which is your pixel pitch. And the pixel spacing, or the distance measured from the center of a pixel to an adjacent pixel, determines your pixel pitch. So when they show you in here the center of one pixel to the center of the adjacent pixel, this is your pixel pitch, whereas the size of the square picture element is actually your pixel size. So both things determine spatial resolution. The size of the pixel and the pitch. The pixel pitch determines the spatial resolution on a digital image. When we look at the spatial resolution, they reference these three pictures at the top of 103. And when you look at those, they reference that this is showing you the difference between pixel size and how it affects your spatial resolution. So this first picture here has showing you an image with 20 pixels per centimeter. So the pixel size is larger, and it has very poor spatial resolution because the accuracy of the structural lines is not really evident. Everything in here looks kind of blurry. You can't really make out the carpal bones in this PA left hand. This is actually the thumb, second digit, third digit, fourth digit, and fifth digit. This is the radius, this is the ulna, and these are all the carpal bones. So this one has 20 pixels per centimeter. Picture B actually has 40 pixels per centimeter. So the resolution is a little bit better, But picture C is actually the best, and this one has 100 pixels per centimeter. So the pixel size is much smaller because remember, each of these is taking 1 centimeter. 1 centimeter in size, and you fit 20 pixels in with picture A, 40 with picture B, and 100 in C. So not only are the pixel size smaller, but in C, the spatial resolution is just incredible. Like now you can the trabecular patterns in the bone. You can actually see the lucency in the bone. You can make out each individual carpal bone, and not only make it out, but you can see where they overlap each other because the resolution is so clear and good on that. So showing you that the more pixels you have, they actually get smaller, and the smaller pixel size and the pixel pitch determines that spatial resolution. By definition, just to let you know, I know it comes up later, but by definition, resolution is the ability of the imaging system to resolve or distinguish between two adjacent structures. And spatial resolution is specific to digital, and it's an evaluation of the accuracy of the anatomic structural lines. Okay, so spatial resolution is actually looking at the accuracy of the anatomy that you imaged, whereas resolution as a whole is how well does that imaging system distinguish between two adjacent structures. They next go into talking about the field of view. And the field of view is basically the dimensions of the area displayed on the monitor. So it's the anatomic area that gets displayed on the monitor. It's actually the dimensions of that display. And they reference that high resolution monitors are required, I've said that before, to maximize the amount of spatial resolution that you can see in the digital image. You can have all the bells and whistles and the highest priced equipment, but if your monitor is not of high quality, then you've wasted your money on the equipment. You're better off to spend decent money on your equipment and more money on your monitor so that you can actually visualize everything that you've paid for in the equipment to capture. Okay? So they reference that there's actually a relationship between pixel size, the field of view, and the matrix size. And they give you this formula. And this is not something that we have to work out now, but I do want you to be aware of what this formula shows. And this formula is on page 102. And they tell us that pixel size is equivalent to the field of view divided by the matrix size. And with this mathematical equation, they tell you that the relationship shows that if the field of view is increased for a fixed matrix size, then the pixel size will also be increased. So it has a direct relationship. So if the field of view gets increased for a fixed matrix, your pixel size will increase. And if your pixel size increases, it takes away from your spatial resolution. But if the matrix size is increased for a fixed field of view, then the pixel size will actually get smaller. So that has an inverse relationship. And if the pixel size is smaller, that gives you better spatial resolution. All right, again, you do not have to work that math out just yet, but further on in your next physics class, you likely will have to work that math, where they'll either give you a field of view and a matrix size and ask you to determine the pixel size, or they'll give you 2 out of those 3 factors and have you solve a third. All right, spatial resolution. This refers to the smallest object that can be detected in an image. All right, and spatial resolution with digital is typically limited to the pixel size. All right, but they tell us in the book that when you're measuring that system's ability to resolve these small objects, it's important to understand the concept of spatial frequency and its relationship to spatial resolution. All right, so spatial resolution is the smallest object that can be detected in an image And remember, resolution by itself is the ability of the system to distinguish between two adjacent structures. So they reference in the book that anatomy is made up of large and small objects, and the images display those structures as variations from white to black or different brightness levels. And smaller objects actually have higher spatial frequency, and larger objects have a lower spatial frequency. Okay, and we're going to look at that in just a minute. So they tell you that it's more difficult to image a small anatomic object with higher spatial frequency compared to imaging a larger object with low spatial frequency. All right, so it's harder to image something smaller than it is something larger, but that's what we're usually looking for on an X-ray, is those small things, the beginning of things, when the tumor starts, not when it's already advanced. So it's important that we have not only good spatial resolution, but you have to understand the relationship of that spatial frequency as well. All right, now I skipped over this, but speaking about spatial resolution, this is called oh my gosh, I just lost it, a resolution tool. And this actually measures line pairs per millimeter. And there's a picture of this resolution tool on page 104 in figure 9.21. Okay. Now, when we talk about spatial resolution, they tell us that in the space of 1 millimeter, the number of line pairs resolved actually determines how much sharpness there is in an image. Okay, so that resolution test pattern, or that resolution tool, can actually record and measure line pairs. And the greater the number of line pairs that are resolved, the greater the resolution. All right. And even when we do talk about the equipment and how well it can resolve the anatomy, realize that the human eye is limited as well. I believe the human eye is limited to visualizing 5 line pairs per millimeter, and that would be a well-trained eye. Likely a radiologist would be able to resolve 5 line pairs per millimeter. Lay people, probably not that well. Just because radiologists are used to looking for discrepancies in patterns or shades of gray. They're used to picking up on those things and looking for those things, whereas a layperson, not so much. So in the space of 1 millimeter, the number of line pairs resolved actually determines how much sharpness there is in the image. Okay. And they reference that an imaging system can resolve fewer line pairs within 1 millimeter, or if it can resolve fewer line pairs within 1 millimeter, like if it can resolve 2 or 3 line pairs, then it has has decreased sharpness. Okay, so if it can resolve fewer line pairs within 1 millimeter, then it'll have decreased sharpness, meaning it won't have very good resolution. So resolution is expressed in line pairs per millimeter. And if it has greater resolution, then it'll minimize the amount of unsharpness of the anatomical structure lines. Because realize that spatial resolution and distortion have an inverse relationship. If something has better spatial resolution, it's sharper, it's crisper, it's clearer, then it's not going to have very much distortion, and vice versa. So you want maximum spatial resolution and minimal amounts of distortion. Now, they said that we need to be aware of spatial frequency. So spatial frequency is defined by the unit of line pairs per millimeter, which we just spoke about as well. Okay, so spatial frequency is defined by the unit of line pairs per millimeter. And this is where we measure resolution. All right, and like I said before, smaller objects have higher spatial frequency, and larger objects have lower spatial frequency. So it's more difficult to image smaller objects, okay, because they have high spatial frequency. Larger objects have lower spatial frequency, so it's more difficult to accurately image a small anatomic object compared to imaging a large object. When you increase the number of line pairs per millimeter that get resolved in the imaging system, you have better spatial resolution, right? And they do tell us that a small anatomic structure is best visualized when the brightness varies significantly from the background, meaning when it stands out more from the background, obviously it's better or easier to visualize. They also go on to tell you that the imaging process itself, because of the fact that the beam diverges in the way the photons pass through the body and the fact that they have the ability to diverge once they pass through, the imaging process makes it impossible to produce an image without some degree of unsharpness. Just because of the nature of what we're imaging, it's impossible not to have some unsharp, because even if your object is as close to the image receptor as it can be, some part of the object is always further away. Like if you put your hand right on the image receptor, then the palm of your hand, the bottom of your fingers, if you put it PA, would be touching the image receptor, but the top of your hand would still be further away. So there's always some amount of OID, or object to image receptor distance, no matter if you are right on top of the image receptor. So it's impossible to produce an image without some amount of unsharpness. Now they go into talking about the modulation transfer function, which is on page 104. Okay, and they reference that an image actually displays a range of brightness levels, which is its grayscale, based on the variations in the radiation intensity tissue. So each of the radiation exits the patient and strikes the IR will have different intensity, different energy, different quantity of those photons. And the anatomy is best visualized when the brightness levels of the object are different than the surrounding tissues, meaning that you have contrast. Usually you want high contrast. So larger objects with lower spatial frequency are more easily visualized. But when the object size gets smaller, it gets higher spatial frequency and becomes more difficult to visualize in an image. So the modulation transfer function is a measure of the imaging system's ability to display the contrast of the anatomic object that differs in size. And the value is somewhere between 0, which means there's no brightness level difference, and 1.0, meaning it's the maximum difference in brightness levels. Okay, so it's a measure of the imaging system's ability to display the contrast of the anatomy of specific objects that vary in size, and it ranges from 0 to 1.0. So if the system has a high modulation transfer function, it can display anatomic detail with improved visibility. But most of the digital imaging systems measure much lower than 1.0. Okay, so if it had a modulation transfer function of 1, there would be 100% difference, and you would absolutely be able to see the difference between the maximum and minimum brightness levels. All right, but no system is going to measure 1, meaning you're always going to have some amount of inability to differentiate the smaller objects from the surrounding tissue. All right, and again, this formula, we don't have to worry about this formula now. I was going to take it out, but this is actually how you calculate the modulation transfer function. Then they mentioned something called the DQE, or the detective quantum efficiency. Okay, I know I did want to say this on the modulation transfer function because this is, I thought I put it on here, but I didn't. So when we talk about it and we said it's a way, the measurement of the imaging system's ability to display the contrast of the anatomy that varies in size, basically it is how well, oh, I didn't put it, sorry, hang on. It's how well the imaging system converts the subject contrast, meaning the contrast that's in the specific patient, to radiographic contrast in the image. The better it converts it, the better it is for the patient and for the radiologist. Ideally, it would be 1.0, but most systems, it's well below that. So it's difficult for the imaging system to take subject contrast and convert it into radiographic contrast. But in a nutshell, that's what modulation transfer function is. Okay, how well does it convert subject contrast into radiographic contrast? Then they talk about the detective quantum efficiency, or the DQE, and you notice there's a lot of acronyms in this chapter. The MTF, the FOV, the DQE, those are all important. So if you haven't already, I would definitely add those to your index cards, because all of these digital terms are something that won't go away and we will see them again. Okay, so detective quantum efficiency is a measurement of the efficiency of the image receptor to convert the X-ray exposure it receives into a quality radiographic image. So it's a measurement of the efficiency of the IR to convert the exposure it received into a quality radiographic image. The higher the DQE of a system, the less amount of radiation exposure it takes to produce a quality image. And if it takes less exposure to produce that image, then that means the patient has less dose. They tell you that if the system could convert the exposure into a quality image with 100% efficiency, there would be no information lost. But no system has 100% conversion efficiency, just like no system has a modulation transfer function of 1.0. That would be ideal, but that's not the case. So the higher the detective quantum efficiency of a system, the less radiation it takes to produce an image, which means less patient dose. Okay? Now we'll go back to spatial resolution. So when we talk about spatial resolution, they tell you that a radiographic image cannot be an exact reconstruction of the anatomy. I said before that it's impossible to create an image without some amount of distortion, basically because of the OID that takes place between the patient or the part and the image receptor. So you can get the maximum amount of spatial resolution when you maximize your resolution and minimize your distortion. That's how your image quality is improved. You want to maximize resolution and minimize distortion because they have an inverse relationship. Okay, maximum resolution, minimal distortion is what your goal is on every image that we take. But you always are going to lose some information when you form the image. Patient motion also. In this image, you can see motion. It looks blurry. This is an elbow. This is actually a right elbow. So this is the radial head right here. This is the radius. This is the ulna. This is the humerus. Okay, but it's blurry, so there's motion in this. That will increase the amount of unsharpness because that is not a sharp, crisp, clear picture. In fact, it's quite the opposite. Okay, and it's hard to minimize how much information is lost by manipulating the exposure factors that affect the sharpness in our image. right? So that's why it's important for us to understand all of these characteristics and qualities that we need and desire so that we can achieve that for the patient and the radiologist. All right, our last factor that is not something we want, it's ideally something we want to avoid, and that is distortion. Okay, so distortion is the result of when you misrepresent either the size of an object or the shape of an object. Okay, so distortion is when you misrepresent radiographically either the size or the shape of an object. And when it's size distortion, it can only be magnification. That's the only type of size distortion you can have. I mentioned this before, you can never make an object smaller than it actually is because of the divergence of the beam. You can make the object true to size, or you can make it larger, but never smaller. So size distortion is where there's an increase in the size compared to the object's actual size. And then with shape distortion, that can appear in two different ways radiographically. You can either elongate the object or foreshorten the object. So size distortion is only magnification. Shape distortion is either elongation or shortening. And if you elongate the part, then you make the part appear longer than it truly is. And if you foreshorten the part, then you make it appear shorter than it truly is. All right, and there's actually two distances that play an important role in minimizing distortion, specifically size distortion, and that is your SID, which is your source to image receptor distance, and your OID, your object to image receptor distance. Both of those distances play a huge role in minimizing size distortion. I had just said a few minutes ago, if you had your hand right on the image receptor, then you would have minimal OID, but still some part of your hand would be further away from the IR than other parts. The SID is kind of a given, but you make sure that you're obtaining the proper SID and utilizing the appropriate OID so that you can get a quality image, because realistically all positioning is based on a maximum SID and a minimal OID. Somebody's already come through and put our positioning book together with realistically almost every position we could possibly take, and everything in there has already been figured out that if you position the patient PA versus AP, or in the left lateral versus a right lateral at a 40-inch SID or a 72-inch SID or a 48 SID, that will give you the maximum amount of resolution and minimal distortion. So our distances play a key role with size distortion. With shape, it has to do more with angulation of either the part or the central ray. All right, now these pictures come from page 106. All right, this picture comes from page 106. And these three pictures are actually the same bone, but it's showing you how you can actually cause shape distortion. Shape distortion occurs when there's a misalignment of the central ray among three factors: either the tube, the part, or the image receptor is not aligned properly. So either the tube, the part, or the image receptor is not aligned, and it will alter the shape of the part, because ideally the tube is perpendicular to the part and the IR, and usually the part and the IR are parallel to each other. All right, let me try and draw that as best I can. So typically you have the tube, which is over your patient, right? So you have an X-ray tube here, and then let's say you have the table, and then underneath the table you have the IR, right? So typically your tube is perpendicular to the part, which would be on the table, and the IR, and then typically your table or your part and your IR are parallel to each other. Okay, so if you misalign any of those, then it can alter the shape. Now realize sometimes we do purposely cause distortion to move anatomy out of the way or to be able to visualize it better, because in the human body, not everything lies independent of anything else. Like everything's, think about a patient's body habitus, like the framework of the body and how all the organs fit in there. Not everything doesn't lay independent. Everything is kind of on top of each other. So sometimes we purposely angle the central ray, or we angle the part, or we angle the image receptor so that we can move anatomy out of the way with the beam in order to get a better visualization of a part. Take, for example, the sacrum. The sacrum is a curved bone at the bottom of the spine, and it's actually curved. Like if you kind of cup your hand, that's the shape of the sacrum. So when we image it, we angle the central ray 15 degrees cephalic, which gives the illusion of the sacrum being flattened out so that the radiologist can evaluate that. So at times we do purposely cause distortion. But if we look at these pictures, this right here, picture A, shows no distortion. Okay, and this is a humerus. So this is no distortion on picture A. Picture B is foreshortened, meaning this same bone is made to look much shorter than it actually is because there was a misalignment of either the tube, the part, or the IR. And then picture C is elongated. So these are all three the same exact part, but they have shown you no distortion, and then they've shown you two examples of shape distortion, foreshortening and elongation, making the part appear longer than it really is and shorter than it really is compared to true to size. All right, so those, before we get into scatter, those four things are what we evaluate in an image. We evaluate the brightness and the contrast to determine how visible is our anatomy. If our anatomy is visible, we then look at how accurately did we represent that anatomy? How accurate are the structural lines in that anatomy? Do we have maximum spatial resolution and a minimal amount of distortion? And if so, if you can agree that all four of those factors are ideal, then you have a diagnostic or a quality or an optimal image. If your brightness and contrast are not sufficient, then there's no need to look at the spatial resolution and the distortion, because if you can't see the anatomy, then we would never care about how accurately we imaged it. So it has to be visualized first and then evaluated for how well you demonstrated that anatomy. Okay. Now, something that we'll take away from the spatial resolution is scatter. Remember that scatter is radiation fog, and it does not provide any useful information about the area of interest. All it does is add unwanted exposure or unwanted shades of gray to our image, and this is the result of a Compton interaction. So Compton, when it adds those unwanted shades of gray, it decreases our contrast, or it makes the visible difference less visible. It makes the changes more subtle. Okay, so picture A up here, this picture comes from page 107, and it's a little bit bigger, so it's easier to see. But on picture A, you have less scatter on this. You can make out the femoral head, you can make out the acetabulum, the ischium, the pubic bone, a portion of the ilium. You can see the greater trochanter on this right femur. Okay, this is actually probably a right hip image. This is the femur, this would be the pelvis. This picture B has more Compton scatter compared to A. So what did it do? It grays out the anatomy. It kind of washes everything out, and it does not make the image diagnostic. You're not able to visualize the anatomy appropriately. When you have less Compton reaching your image receptor, you get improved contrast. You get higher contrast. It raises the contrast. So likely they did this image with a grid, which would eliminate some of that scatter from reaching the IR, and they probably took this as a phantom with no grid. Okay, so scatter decreases or lowers your contrast because it adds unwanted shades of gray to your image. Now, noise. When they talk about noise, again, image noise contributes nothing useful in the way of diagnostic information, and it also detracts from the image quality. Quantum noise is pretty much photon dependent, meaning what happens is you have fewer photons reaching the image receptor in order to form the image. So you end up with this speckled appearance where there's not enough photons creating exposure on your IR. All right, and this picture is actually bigger and better on page 108. So with picture A, they've used the appropriate technique. Picture B, there's an increase in quantum noise because there was insufficient exposure to the IR. Now, when I say that it's photon dependent, I will tell you the only way to correct this is to raise your mass value because you need a larger quantity to strike the part so that you have more photons creating this exposure. So quantum noise is photon dependent, all right? It's brightness fluctuations on the image. That's what this is. All these little spots and speckles are brightness fluctuations in the image because too few photons struck the image receptor to form the image. So the only way to improve and get to this is to raise your mass value. They also talk about, with regard to distortion, things that cause distortion or take away from your spatial resolution. You have your scatter so far we've talked about, our quantum noise. You also have what's called your signal to noise ratio. All right, and the signal to noise ratio, your signal to noise ratio is a way to describe the strength of radiation exposure or the signal in comparison to the amount of noise that's apparent in the image. When you increase the signal to noise ratio, it means that the strength of the signal is high compared to the amount of noise. So when you have an increased signal to noise ratio, that improves the quality of the digital image. But the downside is if that signal is increased, then your patient's exposure was also increased. If you decrease the signal to noise ratio, it means that there's an increase in the noise compared to the strength of the signal. So not so much patient dose, but there's too much noise in the image compared to the strength of the signal. So that's not good either. You really need a balance of that. Okay. Anytime the digital system displays increase in noise, regardless of the source of the noise, the structures will have decreased visibility. So any noise will decrease the visibility of the anatomy. And the last thing they talk about in this chapter are image artifacts. and realize that we can have image artifacts both with film screen and with digital systems. And an artifact is basically any unwanted image on a radiograph. So typically we think of things like jewelry, clothing can cause artifacts, bobby pins, barrettes, braces, glasses, things that you don't intentionally leave on a patient, but sometimes they just happen to, maybe the patient didn't change appropriately, or they didn't hear you say that they needed to remove something. That would create an artifact, basically something unwanted on your image. And they can be detrimental because it makes the visibility of the anatomy more difficult, makes it harder on the radiologist to actually read the image, because he or she can't visualize all the anatomy that they need to. When we look at some of the digital image artifacts, this picture is actually on this page 110, and they show you the bright lines they reference in the shoulder image on this pediatric chest are a result of scratches on the actual imaging plate. So this is not something in the patient, it's actually a result of scratches in the imaging plate. But if the radiologist wasn't aware of that, he or she could actually read that something within the patient or question what that is, which might warrant further testing or further imaging to look at that, when in reality there's a scratch on the image receptor. In this picture of the left hand, they reference that there's bright specks in between the fourth and fifth metacarpal, which this is the fourth metacarpal, this is the fifth metacarpal. I honestly have a really hard time seeing the specks. Even in the picture in the book, it is difficult, but they reference that the bright, those little specks that are in there, is actually dirt on the imaging plate. Okay, so those kind of things can make it detrimental for a radiologist to actually read the image and look at the anatomy if there's artifact on the plates or on the patient. If we leave things on the patient that we shouldn't, like jewelry or pierce. If you ever have a patient that you know has artifact on them and you ask them to remove it and they refuse, that's fine. You simply need to note that they left their necklace on, or they refused to remove their jewelry, or they were unable to remove something. I've had patients that can't take off jewelry because they've just had the piercing done, or it was very sentimental and they never take it off, which is fine. You just need to note that so that the radiologist can dictate it, so that there's no question as to why that was actually left on. Okay, so these are just some of the digital artifacts. Typically, when they talk about artifacts, they usually classify artifacts into two categories, which are either plus density or minus density artifacts. When it's a plus density, it will appear, the artifact will appear darker than the area surrounding it, meaning plus density plus darkness. When it's minus density, they appear brighter or lighter than the area surrounding it. So when we looked at this pediatric chest a minute ago, this would be a minus density artifact, okay, because it appears bright in comparison to the anatomy around it. I do not have an example of a plus density artifact, but it would just appear the opposite way. So usually artifacts are categorized into either plus density or minus density artifacts, and realize that digital can have a lot of different artifacts compared to film. It just depends. Usually you have to try and figure out how it was created. So looking at the imaging plates, occasionally cleaning those plates is important. And the imaging plate is inside the digital receptor, so those do have to come out sometimes and actually be cleaned. If a plate is damaged, noting that so that people don't reuse that plate until it's repaired is important. All right. And that takes us to the end of chapter 9, part 2. If you have any questions or comments or concerns, please be sure to write those down, and hopefully the next time we meet, I can help clear that up. All right, and that's the end of that. Thank you so much.